2, 1. Hello, I'm Boston Zachmann.
And I'm Andrew Krecklau.
And I'm at Ruhland.
And this is our ECE476 final project. We built a system that goes on top of a model rocket that helps stabilize it during flight. Okay, it's like a general overview of how this thing works. Basically, there's two axes of rotation that we care about. One of them's the y-axis and one of them's the z-axis. With respect to what the IMU gives us, basically, if it rotates on this axis, the same degree of deflection that it rotates, the fins or the servos will correct. This is to get a perpendicular fin basically at all times. If it's flying like this, it's going to catch some wind resistance on these wings and kind of straighten the rocket, and as it straightens, the fins will correct back. So that's the idea about how that's going to correct flight if it works. So here's the rocket in our 3D modeling software. We use Google SketchUp to 3D print the enclosure. I just wanted to give you a quick look inside and see how everything is laid out. Here you can see we have this servos mounted to some 3D printed walls in the inside. And then you can see here's our IMU and our button. And then down here, this is our Adafruit Pro trinket, and then our SD card, and then our battery sits underneath that. So everything was printed out and glued together. And here are just some pictures we had taken before we put everything inside the rocket tube. We just wanted to include those here. It's pretty tricky to get everything soldered together and put into such a small space, especially getting all the wires and the servos to fit in the upper compartment. And there you can see the modified rocket tube, and there it is with servos in it.
Okay, so taking this apart, on the bottom of our rocket we have our components we can see. First off is our power port sticking out right here, and then our battery we have on the right side. We'll just plug it in when we need to power it. And right here is our Hall effect sensor. We'll be able to detect when this is off of our rocket, when it is at the top of the flight and disconnects. Our magnet is in there, you can see. And then on the left side here we have our SD card for logging flight data during our flight. And then on the right side is our microcontroller. And if we go to the top, under the cone here, we have our IMU, giving us our sensor or orientation data, and then a button for a couple of features we'll explain later.
So first thing we have to do is plug the device in. Now that it's plugged in, it's in a bootloader right now, and there you can see now it's out of the bootloader. I don't know if you saw that fin move. But it sits in this situation, or in this state, until we have time to actually put the device on the rest of the rocket. Once we do that, we press this button to kind of allow it to continue setting up and get to its main loop state. So there, now it's actually running. You can see now that the fins are actually moving and adjusting to angles. You can see here's some limits where they're not going to touch even if we're almost completely horizontal here. So yeah, that's showing some of the updating and the correcting that's happening. Here you can see as soon as we remove the system, after I think it's 300 milliseconds is what I coded in, of detecting that this Hall effect sensor is gone, everything shuts down and it straightens the fins.
So these are some of the internals of the rocket. This is the parachute. It's connected to both sides of the rocket. We did cut a hole in the top portion of the parachute. You can see right there. And this will allow it to drop a little bit faster that we don't have to wait as long, but it'll still manage at a reasonable speed so we don't break any of the components. So these are some examples from a logged file that we have from our SD card. The first column, that's all zeros, is for future development to track the spin of the rocket and potentially correct that. That'll be for future development of this project. The second column is for the y-axis deviation. So if we start, it'll be whatever degrees we are different from that. So for example, this is 30.62 degrees. And the third column is for our z deviation. So this is negative 15.0 degrees. So when we have all of these flight recordings on the SD card, we can model them in Excel and then potentially see how much of a difference we can make with the correction of the rocket.
Okay, so right now we have it on, and so right now it'd be correcting flight to go straight up. We can see it changing the with respect to each axis. Another feature we added though with this is with our button is that if we hold it for 1.5 seconds, we can set it to an intended line of flight. So what I'll do is I'll hold the button down here, and we'll intend for it to go this way. And now you can see it will be correcting for this line of flight. If we change it, you can see the fins moving to correct for those changes.
So you can see here that every now and then the fins will jitter a little bit. See that? We found that this issue happened when the I2C was being used to communicate to our IMU. And what you would normally do in this situation is correct it in hardware. What's happening is there's noise being caused on the PWM lines that are controlling the servos. But in this case, we found that out after everything was in here and, already permanently in the rocket tube. So there was really nothing we could do here. But for future uses, that's what you would do. Alright, now it's ready to launch.
That finger dexterity.
Look at that. Ready? 3, 2, 1. Alright, so good news is nothing broke. It came down safely. We retrieved it. It looked from our perspective up there that it looked like it went kind of way to the south, I guess, way too far, but from Andy's perspective it looked like it kind of went pretty much more straight than it was actually angled. So this run we're going to put it at a pretty big angle and see if it goes straight. Alright, so here you can see we have our stand. Pretty big angle. We're going to launch it like that and see if it corrects and goes up. Ready, Andy? 3, 2, 1. Okay, so we just got done with our second launch, recovered it. It's gonna have to be a day though. This servo maybe is a little bit messed up, and this wing broke off. I don't think that happened during flight or at the top of its flight or anything. I think it happened when it actually hit the ground. It was coming down pretty fast. what happened was our parachute kind of melted together. On that one I used some different wadding than I used on the first one, so it's probably just some old wadding I had, and it just ended up, heated it up too big. And you can see it, I can see that the inside of the barrel, or the tube, is also a little bit more charred than it was before. So it's probably gonna have to be done, be it, because I don't know, I don't think this is gonna come apart very nice. We don't have another parachute, so.
This is day 2 of our launch. Last time we were able to correct the angle, we were able to correct the rocket against the wind. This time we're going to launch it with the wind and see if it can correct it. So we'll give that a go.
So this time we're going to try it with the fins locked in place at the same trajectory as Flight 3. This will be our control test to see what our data would look like.
So these are the results we obtained from our SD card after launch. At the beginning of the flight, while it was on the launch pad, it's at negative 10 degrees deviation for our Y and our Z axis. And then shortly after launch, which starts around second 41 there, it corrects, but it also overcorrects and goes past the 0 point, and it goes up to around 10 degrees on the Y and about 8 degrees on the Z. And then it kind of levels off, and then it starts overcorrecting again. So that's the kind of general theme we found with all of our launches, is that it corrects, but then it kind of does an overcorrecting back and forth throughout the launch. But I still think that's pretty good. You'll see in the next test launch results that it indeed does correct. It just does a little bit of overcorrecting and jumping back and forth when it's around 0. And you can see around 46.2 seconds is right when it's kind of hitting the top of its flight, and the engine's kind of fizzling out. And then so it kind of goes kind of crazy up there, and then around 47.4 seconds the parachute is coming out, so that's just some garbage data up there. And these are the test results for test launch 2. You can see it starts at a deviation angle, a much greater deviation angle than before. That's because we started it at a big tilt angle. And then you can see around 62.4 seconds is when the rocket starts to launch. And there's that big spike up, and then that big spike down on the Z-axis. And that's caused by a rotation of the rocket. So the fin is going from, if the rocket is a 180 degree turn, one of the fins on the side has to go from all the way corrected upwards to all the way corrected downwards, and vice versa for the other fin. So that's what is causing that. But you can see, if we just ignore that, because that's caused by rotation, from around 63 seconds onward, it does kind of correct towards 0 degrees deviation. And again, it floats and kind of overcorrects, not as much on this run, but it does overcorrect around 0. So just kind of slight wobbles up until, again, 67.8 seconds, where the end of the run starts to happen. And then the rest of the data is just kind of garbage data. And finally, the results for test launch 3. So this was again the angled launch, but this time it was with the wind instead of against the wind. One thing to note is you can see even when it's on the launch pad, the deviation you can see it's it was a pretty strong wind that day, a lot windier than on test launch too. And you can see the launch pad is even moving a little bit, and the rocket's moving on the launch pad. And then when test launch start, again, you see the around 124.25 seconds. There's that drop. Again, that's caused by that rotation happening. But then you get a pretty smooth correction almost immediately to around 0 degrees. And you can actually see this in the video if you want to back up and watch it. You can see it's a very immediate correction on this run. And then it does that oscillation motion. And the interesting on this one is it actually gets worse, and then it kind of dies down. So I'd like to say that this was in part due to either the way we were launching with the wind or the fact that it was a lot windier that day. It was applying a lot more forces on the rocket, and it wasn't as smooth as the day before. So, and then again, so it does that oscillating motion up until around 120.75 seconds, and then again it fizzles out, and the rest of the data is not useful. And unfortunately, we do not have any flight data for launch 4, the launch where we launched at an angle without any correction happening on the fins. It was pretty apparent from the video alone that it went at that angle pretty much its entire flight until the end when it started to drop even more. And it didn't correct at all. It didn't move upwards to go straight up. So we could say that's a success without the data, but unfortunately the software was set up to log the deviation of the data, and to get the fins corrected to just stay straight, we were just setting the deviations directly to 0 so that it would not correct, and in doing so it was just logging zeros. So that was just a little oversight on our part, but it would have been nice to see the data, but it wasn't necessarily needed in this case. And for the final part of this video, I have some software flowcharts on there. The first flowchart was the setup. The second flowchart, the one you see now, is the main loop, and the one coming next will be the interrupt handler. So feel free to look through those and study them if you want to learn how the software was working.